Hello everyone. The title of this presentation is Flexural Ductility of Concrete Beams Reinforced with High-Strength Steel. My name is Sohaib, and with me are co-authors Professor Michael Bartlett and Professor Magid Youssef. The current CSCE standard for 823.3 concrete design limits the yield stress for reinforcements to 500 MPa. And the objective of this research is to update this code because high-strength reinforcement has a yield stress well above 500 MPa. So we'll be comparing the flexural ductility between conventional and high-strength reinforcement. And in doing so, we'll also verify the existing target reliability indices to see if they are a good representation of high-strength reinforcement or if they need to be updated. So you can see the cross-section of a beam that was used in this research. The variables here were the concrete compressive strength, the tensile reinforcement type, and the area of steel. Corresponding to this, we have the moment curvature, with curvature plotted on the horizontal axis and moment on the vertical axis. So this curve is typically bilinear, the first slope representing the elastic portion of the beam and the second slope representing the plastic portion when the steel has yielded. You can see the 2 points labeled here, which are the yielding point and the ultimate point. And we'll be talking a lot about curvature ductility, which is the ratio between ultimate and yielding curvatures. The assumptions made here were that the plane sections remain plane, which means that the strain in the beam is linearized, and secondly that the beam and the reinforcement have a perfect bond. As for the method for computing moment curvature, for a given extreme fiber strain, we compute the neutral axis depth, and from there we can find the strains, the stresses, as well as the forces in the concrete, which is the compressive force, and in the steel, which is the tensile force. And we sum them, and if we find that the force is not equal to 0, then we check if the compressive force in concrete is smaller than the tensile force in steel. And if that's true, then we increase the neutral axis depth, and if that's not true, then we reduce the neutral axis depth. Now once the forces are 0, we can proceed and we can find the moment, and we check again if the moment in the current iteration is smaller than the previous moment in the last iteration. And if that's true, then we stop because we have achieved the maximum moment. And if that's not true, then we increase the extreme fiber strain. As for the concrete idealization, the one we used was Q 1985, which is a function of Fc prime, which is the concrete compressive strength, and epsilon C, which is the concrete strain, and epsilon naught, which is the strain corresponding to Fc prime. And we also have beta, which is a function of Young's modulus and Fc prime. And we use multiple idealization and plotted the stress strain curve, with strain plotted on the horizontal and stress plotted on the vertical axis. So the idealizations considered were Thornfield and Hui. And as you can see in the graph, up until the strain corresponding to the maximum stress, the curves are similar, but after that point there is a divergence in the plots. So we used Chu in our research because it is a well-known idealization that's used in many research. For the steel reinforcement properties, we have different grades like A615 grade 60 and grade 100, A706 grade 60 and grade 80, and A1035 grade 100. The different parameters were the yield stress, the ultimate stress, the ultimate strain, the strain hardening parameters. And we use these parameters and inputted them into the steel idealization by Manders and Matamoros in 2019. And the first term here is the elastic portion, and the second term is the plastic portion with strain hardening properties. So the stress strain curves for different reinforcements were plotted using this idealization. And you can observe that the yielding point is distinct for almost all of these reinforcements, apart from A1035 grade 100, which is exhibiting a roundhouse behavior. So our data was then validated with Yosefani, who conducted a research that was experimental for A615 grade 60. And looking at the yielding and the ultimate points from that experimental data, we can find the yielding and ultimate loads. And for ultimate load, we get 104 kilonewtons with a corresponding mid-span deflection of 42 millimeters. Then looking at our data and looking at yielding and ultimate points, we get an ultimate load of 101 kilonewtons and a corresponding deflection of 47 millimeters. So these two curves are fairly close to one another, and ours is a bit more conservative because we get higher deflections, and that's always good for design. We also conducted sensitivity analysis, so the variables we changed were the steel area, adding compressive bars, increasing or reducing the FC prime, as well as changing the yield stress in reinforcements. So the red curve, which is the control, was a beam reinforced with grade 60 reinforcement with given moments and curvature ductilities, and we saw the changes in percentages. So for example, when we reduced the seal area by half, we got a 45% reduction in moment and 108% increase in curvature ductility. Doubling FC prime gives us a insignificant moment, but 120% increase in curvature ductility. When we increase the yield stress by 25%, we get about 20% increase in moments and a 35% reduction in curvature ductility. And lastly, once we add two 10M compressive bars in our beam, we get almost no change in moments and about a 10% reduction in curvature ductility. We also changed the FC prime values. The curve on the left, you can see that the ultimate curvatures are increasing with increase in FC prime, but the yielding curvatures almost stay the same. So for an FC prime of 30, we get a ductility of 1.8, and for 70, we get a ductility of 2.8. And the relationship here is that once FC prime increases, the neutral axis depth would start to decrease, and curvature ductility would increase. So there's an inverse relation between curvature ductility and neutral axis depth. For a 1035 grade 100, as I previously stated, it is a roundhouse curve. So we had to convert it into a bilinear curve, and the approximation was based on taking the tangent of the elastic portion of a 1035 and picking a point on that tangent and moving it around such that the areas enclosed by the bilinear and actual curve were equal and equated to 0. And we picked that point as the yielding point. And then we plotted the mechanical reinforcement ratio on the horizontal axis and the curvature ductility on the vertical axis. And basically, if we were to look at a reinforcement ratio of 0.1 and observe the curvature ductilities, we can see that A615 grade 100 has the smallest curvature ductility of 4.9, and A706 grade 60 has the highest curvature ductility of 9.3. The other three reinforcements, the A615 grade 60, A706 grade 80, and A1035 grade 100, have fairly close curvature ductilities between 7 and 8.8. So in conclusion, the curvature ductility is the inverse of mechanical reinforcement ratio. A615 grade 60, A706 grade 80, and A1035 grade 100 have similar curvature ductilities. A706 grade 60 has the greatest curvature ductility, and A615 grade 100 has the smallest curvature ductility. And because it's small, we need a more stringent target reliability index for A615 grade 100 to calibrate a resistance factor for the updated code design. I would like to thank Natural Sciences and Engineering Research Council, as well as A23.3 High Strength Reinforcement Task Force. Thank you.